300 million years ago, the world's air wasn't just different, it was lethal, exhilarating, and utterly alien. Earth's atmosphere swelled with 35% oxygen, a chemical jackpot that fueled forests taller than skyscrapers, and insects so huge their wings cast moving shadows over the land. Fires could ignite in damp wood, and a single spark could bring an entire ecosystem to its knees. For 60 million years, life adapted and sometimes surrendered to this hyper-oxygenated empire. But what unleashed so much oxygen, and how did it transform every living thing? The answer lies buried in the coal swamp jungles and strange chemistry of the Carboniferous world, where each breath changed the fate of the planet. Step into the heart of a Carboniferous forest. Towering lycopsids, ancient relatives of today's club mosses, rise 30, sometimes 40 meters overhead. Their trunks are straight and scaly, branching only at the very top, where crowns of long, narrow leaves catch the filtered sunlight. The canopy is so thick, only a dim green glow reaches the swampy ground below. Beneath your feet, the soil is not soil at all, but a dense, waterlogged mat of peat, layer upon layer of dead plants pressed and preserved by endless humidity. Every year, this peat thickens by 0.5 millimeter, sometimes more, as fallen trunks and fronds pile up faster than they can rot. In places, the buildup is so relentless that entire forests seem to stand on their own composted ancestors. The air is heavy with the scent of living and decaying leaves. Tree ferns and horsetails crowd the understory, their fronds arching above mats of moss and tangled roots. Roots snake out sideways, rarely plunging deep because the ground is saturated. Oxygen-starved, dark and perfect for trapping organic matter. The forests stretch for hundreds of kilometers, blanketing the lowlands of Epochs and ancient continents. In these vast, unbroken mires, carbon is locked away by the ton, and the atmosphere above begins to change. With each generation, the coal swamps act as a living engine, drawing carbon from the air, building forests faster than decay can reclaim them, and setting the stage for an oxygen-rich world that no creature today could survive. Lignin, the tough molecule that made these forests possible, was both a blessing and a curse. Plants built their trunks and branches from it, stacking carbon into woody tissue that resisted decay. But in this ancient world, the usual suspects, fungi and bacteria, lacked the tools to break lignin down. White rot fungi, the master decomposers of modern forests, simply did not exist yet. As a result, fallen trees and leaves did not rot away. They lingered, layer after layer, becoming peat, then coal. Every year, more carbon was locked underground, and the chemical balance of the planet began to tip. The numbers are staggering. Models like GeoCarbSulf, built by geologist Robert Berner, show that as forests buried billions of tons of carbon, oxygen was released into the air in equal measure. The process was relentless. Photosynthesis split carbon from CO2, plants grew, died, and instead of returning to the atmosphere, their carbon stayed trapped below. Oxygen, the byproduct, had nowhere to go but UP. Without decomposers to close the loop, oxygen built up in the sky for millions of years. Geochemical records and fossil charcoal confirm the trend. Rising O2, falling CO2, and a planet remade by a simple chemical bottleneck. The world was running a planetary experiment. What happens when carbon burial outpaces decay? The answer was an atmosphere supercharged with oxygen, ready to reshape the future of life. Eyes the size of marbles, wings as long as a crow's, and a body heavier than a modern songbird. This was Meganeura, the aerial giant of the Carboniferous skies. With a wingspan stretching up to 75 centimeters, it soared above the swampy forests, hunting anything it could snatch mid-air. Its 4 wings moved independently, giving it the power to hover, dive, and turn with a precision that modern dragonflies can only hint at. Fossilized thoraxes show a muscular, skewed frame designed for forward flight, a living net cast across the canopy. On the forest floor, another titan moved with slow, armoured confidence. Arthropleura, a millipede stretching up to 2.5 meters, longer than a grown man, slid through the tangled roots and moss. Its body, segmented and plated, was built for pushing aside ferns and fallen branches, feeding on the endless supply of decaying plant matter. No modern arthropod comes close in size or presence. The secret behind these giants lay in the AR itself. Insects don't breathe with lungs. Instead, a network of tiny tubes, tracheae, delivers oxygen straight to their tissues like millions of microscopic snorkels. Normally, this system limits how big they can get. The farther oxygen has to travel, the less reaches the core. But in a world with 35% oxygen, the rules changed. Laboratory experiments at Arizona State University proved it. When modern insects are raised in hyper-oxygenated air, they grow up to 20% larger, with thicker bodies and wider wings. The Carboniferous atmosphere was a biological amplifier, letting simple designs reach monstrous proportions. Yet this size came with a catch. Their very existence depended on the sky staying rich in oxygen. The age of giants was always at heart an age of breath. One spark was all it took. In a world where the air carried 35% oxygen, even the dampest forest could become a tinderbox. The very atmosphere that let giants breathe also set the stage for disaster. Lightning struck, and what should have been a harmless flash became a chain reaction. Flames racing through peat, up the trunks of lycopsids, leaping from fern to fern. Fires didn't just smoulder in the undergrowth. They roared through the canopy, fueled by oxygen so rich that even living, water-soaked wood could catch and burn. Charcoal tells the story. In places like the Upper Millstone Grit of Britain, thick bands of fossilized charcoal slice through the rock, each layer a record of forests consumed by wildfire. These aren't isolated events. Charcoal beds are stacked one atop another, evidence of firestorms that swept the Carboniferous lowlands again and again. Soot particles embedded in ancient sediments match what's seen after today's most intense blazes, but on a scale that dwarfs anything in recorded history. The rules that protect modern forests, moisture, green leaves, even standing water, offered little defense. At 35% oxygen, the ignition threshold collapsed. Fires could start in rain-soaked woods, leap rivers, and burn for weeks. The forest, built by relentless growth and carbon burial, now faced an enemy that struck without warning, erasing centuries of life in a single season. Every blaze sent carbon skyward, chipping away at the balance that made this world possible. In the Carboniferous, fire was not just a hazard, it was a force of nature, waiting for its moment to turn paradise into ash. The illusion of endless forest shattered in an instant. Around 305 million years ago, the coal swamps began to fragment, breaking apart the vast, unbroken green into isolated pockets. Fossil root beds at Joggins, Nova Scotia capture the moment. Giant lycopsid trunks preserved upright, their roots splaying through ancient mud, suddenly cut off by layers of sand and silt. What had been a continuous, humid expanse turned patchy and dry as climate shifted and sea levels fell. The ground, once waterlogged and stable, became prone to flooding, erosion, and drought. Swamps retreated, leaving behind stranded forests and exposed peat. The collapse wasn't gradual, it was a tipping point. With the rainforest gone, the engine that had pumped oxygen into the sky began to sputter, and Earth's atmosphere started to change course. White rot fungi arrived quietly, but their impact was profound. These organisms unlocked the secret code of lignin, wielding powerful enzymes, lignin peroxidases, that could break down the toughest wood. For the first time, fallen trunks and ancient peat could rot away, returning carbon to the atmosphere instead of locking it underground. This biochemical breakthrough spelled the end of the coal forests and sent oxygen levels plummeting. In the patchwork landscapes that followed, a new kind of survivor took center stage. Early reptiles, wrapped in scaly skin and armed with the amniotic egg, could lay their young far from water. They thrived in the drier, changing world, gaining a foothold that would shape the next age. The lesson lingers. The rise of decomposers and the innovation of reptiles weren't just evolutionary accidents. They set the boundaries for what life, and even a planet's atmosphere, could become. On distant worlds, a spike of oxygen might hint at forests without fungi, or a biosphere still waiting for its next great innovator. At its peak, Earth's atmosphere reached 35% oxygen, nearly twice today's level, a figure confirmed by fossil charcoal layers and coal deposits spanning 60 million years. This hyper-oxygenated world allowed insects like Meganeura to reach wingspans of 75 centimeters and fueled wildfires powerful enough to leave thick charcoal beds in rocks such as the Upper Millstone Grit. The collapse of these coal forests around 305 million years ago, triggered by climate change and the evolution of lignin-degrading fungi, ended the era of giant arthropods and set atmospheric oxygen on a downward path. While the exact timing and pace of these changes remain subjects of ongoing research, the evidence shows how life and air shaped each other in dramatic ways. Today, the coal and fossils left behind are direct records of this ancient world. The Carboniferous period stands as proof that the composition of our atmosphere has always been the product of life, and that its changes can reshape the planet.